In this recording, we are going to discuss the excess Gibbs free energy and its relation to the activity coefficient. We are going to model the liquid phase behavior of the mixtures in relation to a vapor-liquid equilibrium problem solving. So before we can arrive at Gibbs free energy and excess Gibbs free energy, we have to remember the partial molar properties. Partial molar properties are the contributions of the properties in a mixture in opposition to their pure fluid behavior. If the volumes are additive, we can use the pure fluid behavior to estimate the total fluid volume. If the energies, enthalpies, are additive, we can use pure fluid enthalpies to estimate the mixture enthalpy. However, this is not always the case. The mixing may result in a volume that is different from the net sum of the weighted sum of the individual contributions from the components, and energy interactions between the molecules, constituent molecules of the different species, may result into the net final enthalpy of the mixture, which is different from the weighted sum of the individual constituents. In order to take that into account, we are using a property called the partial molar property. Partial molar property is different from the molar property in the sense that the molar property is the pure fluid property of the component. Partial molar property is the contribution to the mixture from that component. So remember that when we added two mixtures together, let's discuss this through an example, that when we added two same volumes of different components, for this particular case, let's have the total volume be less than 2V. Still, we need to find out the contribution of A to this total volume and contribution of B to this total volume, so that we can find the final total volume as the summation of these partial volumes. And we can only arrive here from the information that we gather about the total volume through some mathematics. And the mathematics go in the general symbolic equations that I have written here. Theta represents any molar property. The molar property of the mixture is the summation of the partial molar property of the individual constituents multiplied by their mole fractions. Partial molar properties of the individual constituents multiplied by their mole fractions summed up. And what is this partial molar property? Partial molar property, by definition, is the partial derivative with respect to the number of moles of that particular component of the total property. So, if, look at this example, if I have total volume, which is total number of moles times the molar volume, the partial derivative of this with respect to the number of moles of A is going to be my partial molar volume of A. So this partial derivative, if we work through the algebra, this partial derivative is going to be V times del N over del NA. And of course here I'm keeping everything, temperature, pressure, and NB constant when I'm taking this partial derivative. V times del N over del NA, T, P, MB constant, plus N times del V over del NA, temperature, pressure, and NB constant. Let's take the derivative of N with respect to NA. N is equal to NA plus NB and therefore del N over del NA, keeping temperature, pressure, and NB constant, is going to be 1. This is going to be 1. This is going to be 0. Here, the derivative of N with respect to NA, keeping everything else constant, is going to be 1. Now, let's take the derivative of V with respect to NA. V is equal to XA times VA plus XB times VB. XA is NA over NA plus NB. XB is equal to NB over NA plus NB. As you can figure out, this partial derivative is going to be about taking the derivative of XA with respect to NA and XB with respect to NB. All right? So the algebra is going to be left for you, and you are going to show that really we recover the partial molar volume by taking this derivative and going through this algebra. So this is the whole concept of partial molar property. It is the contribution of A in a mixture to the total volume. So then we have made the definitions of ideal mixtures. What is an ideal mixture? Ideal mixture is where the partial molar volumes are equal to the molar volumes. In other words, there is no change upon mixing. And partial molar enthalpies are equal to molar enthalpies. In other words, there is no energy interaction upon mixing. Our limits is finished with volume and enthalpy. When it comes to entropy, we have a different we have a different definition. The equation on the board was not accurate, so I have cleaned it up. Let's clean it up a little bit more. Now it is good. So the partial molar enthalpy for an ideal mixture is equal to the pure component entropy. Pure component entropy minus the entropy that has arisen as a result of the entropy that has arisen as a result of mixing two components. That equation needed a lot of rectification. All right, so when we take this one and write the entropy, total entropy of the ideal mixture, it will be the total entropy due to the pure component entropies total entropy due to pure component entropies minus R xi ln xi. So our previous equation was falling in between the total entropy and partial molar entropy. All right, so for an ideal mixture, so this is pure component entropies, and this is the entropy because of the mixing. When we are mixing two dissimilar materials, we need to take the entropy effect upon mixing. It's just a matter of probability of finding a molecule in a space in a pure component. That probability is unity. In a mixture, that probability is less than 1, and that term takes that probability into consideration. So when we start from this, we can now start writing the Gibbs free energy of the ideal mixture of component I that is going to be this time Gi, pure component Gibbs free energy, plus this time RT ln xi. And this is due to the fact that Gibbs free energy is enthalpy minus T times entropy. We have no contribution from enthalpy for an ideal mixture, but the entropy contribution comes through this equation. So the ideal mixture Gibbs free energy is equal to the pure component Gibbs free energy and the contribution that is coming from the entropy. For the total Gibbs free energy of this ideal mixture, we're going to have summation over all species And now we have pretty much full set of the thermodynamic variables. Let me just write Helmholtz free energy. It also follows the same rules with the Gibbs free energy. And of course, its partial is G replaced with A. This is the ideal mixture situation. The real fluid situation is going to be different. Real mixture situation is going to be different from the ideal mixture situation. And the difference between the real and the ideal mixture is going to be called the excess. So the definition of the excess property is going to be, again, in the general theta terms, the excess property is going to be the difference between the partial molar property to the pure fluid property. So excess volume in an ideal mixture is going to be 0. Excess enthalpy in an ideal mixture is going to be 0. Excess entropy in an ideal mixture is going to be Rln xi. Excess Gibbs free energy in an ideal mixture is going to be RT ln xi. So if we just sum this up, overall species we get the total excess that is going to be xi times the partial molar property minus xi times the molar property of the pure component. All right, so this is theta I, all right, the total of it, and this is theta of ideal mixture. Okay? So from here we are going to derive the excess Gibbs free energy, partial molar excess Gibbs free energy, and relate that to the activity coefficient. Now that we have made the definition of the excess property, we are now going to translate that into the excess volume upon mixing of component I. So the excess partial molar volume of component I, let's just use it for the superscript because for the subscript we need the species identifier, is going to be the partial molar volume of I minus molar volume of I for a pure component. So partial molar excess volume is going to be the difference between the partial molar volume relative to its counterpart molar volume of the pure component. All right? So this is going to be very useful in the sense that when we are trying to estimate the mixture properties, we will have a domain that is at our disposal, the pure component property. If we can somehow take the difference beyond the ideal or beyond the pure component into account, that is going to save a lot of mathematics on our part, and it's going to improve our estimations. So, of course, the excess partial molar volume is going to be 0 for an ideal mixture, because for an ideal mixture, our molar volumes are equal to our partial molar volumes. Excess enthalpy of component I is going to be the partial molar enthalpy minus partial molar enthalpy of the pure component. So the excess volume is going to be the difference between the partial molar volume of component I minus the ideal pure component. Excess enthalpy is going to be the difference between the partial molar enthalpy of component I in that mixture minus the pure component enthalpy. Excess entropy, excess partial molar entropy will be the partial molar entropy of component I in that mixture minus the pure component entropy plus Rn and Xi, the entropy due to mixing. Similarly, excess Gibbs free energy, partial molar excess Gibbs free energy of component I is going to be the difference between the Gibbs free energy of that component in that mixture, partial molar Gibbs free energy of that component in the mixture, minus molar Gibbs free energy of the pure fluid minus RTL and Xi, minus comes from the definition of Gibbs free energy in relationship to enthalpy and the entropy. This excess Gibbs free energy is going to be reflected in the definition of the activity coefficient. So let's start from this excess Gibbs free energy and define some steps. So I'm going to define this as G I ideal mixture to save time and space. So this is going to be Gi minus G ideal mixture. Now I have brought this to a difference between a component in a mixture minus component in an ideal mixture. What I'm going to do is I'm going to add and subtract the Gibbs free energy of partial molar Gibbs free energy of an ideal gas. All right, ideal gas state is my reference state. Let's see where this algebra is going to take us. I'll just combine these two and then these two. Gi minus Gi ideal gas minus, I'm going to have G ideal mixture minus G ideal gas. I hope that now you can, at this stage, you can differentiate the ideal mixture property from the ideal gas property. So we are going to substitute the fugacity equivalent expressions of each of these parameters, and let's remember fugacity of component I in a mixture, it was equal to exponential of Gibbs free energy. The partial molar Gibbs free energy is going to correspond in an ideal gas state, is going to correspond the mole fraction multiplied by pressure equivalent. All right, so let's just put that in writing here. So that our term here is going to be ln of Fi divided by xi times p. And the term, so we're going to resort to the definition of the Gibbs free energy in the ideal mixture. All right, this is going to be pure component Gibbs free energy plus RT ln xi, and the Gibbs free energy, partial molar Gibbs free energy of the ideal gas is going to have similar definition. We're going to subtract to cancel these two. Here we are going to have the difference of the pure component in relation to its ideal gas counterpart. And that difference is going to be RT ln Fi over P. So putting our RT here that we have forgotten before, minus RT ln Fi over P is going to be, when we combine these two together, RT ln Fi over Xi times Fi. This is the fugacity of component I, which is a function of temperature, pressure, and the mole fraction of all the components. This is the fugacity of its pure counterpart, and we are comparing this pure component against its contributed one to the in a mixture. And that is going to be the excess Gibbs free energy definition related to the fugacity. So here, we are going to also relate these to the fugacity coefficients of the individual components in a mixture and in pure state. And of course, this is going to be back to our definition of fugacity and Gibbs free energy, V dP. So this, of course, at constant temperature, this is going to be estimated from an equation of state. The PVT relationship can allow us to carry out this integration without much trouble, but it will be, of course, with a lot of effort, as long as a PVT relationship exists. If PVT relationship does not exist, if a good PVT relationship does not exist, then we are going to use a term called activity coefficient, gamma I. So we are going to convert the fugacity relationship Fi into Xi gamma I Fi. So this is going to be our correction factor. So now on a clean board, let's reiterate our derivations. Partial molar excess Gibbs free energy is derived as RT ln fugacity of component I in a mixture divided by pure component fugacity multiplied by its mole fraction. This is equal to RT ln of fugacity coefficient of the component divided by the fugacity coefficient of the pure species. This is equal to an integral between 0 to the desired pressure, the difference between the partial molar volume minus molar volume of the pure component times dP. This is the definition of the excess Gibbs free energy, and we have also introduced a new term called the activity coefficient gamma I. Gamma I is going to allow us to relate the pure component fugacity in the liquid phase to the fugacity of the component I in a mixture as a correction factor or as a modifier. This is going to be multiplied by the mole fraction. If we are going to have an ideal mixture, this is going to be drop out of the equation, as we have done with the Raoult's law derivation in an earlier video. Now let's substitute this here to relate the activity coefficient to the excess Gibbs free energy, excess partial molar Gibbs free energy. Over RT is going to be ln of Fi. I'm going to indicate precisely that this Fi is a function of temperature, pressure, and the composition of all the components in the mixture. This Fi is going to be substituted through this equation, FIL, pure component fugacity, gamma I, mole fraction of I, divided by FIL xi. Right? As you see, these terms are going to cancel. And now we related the activity coefficient to the excess Gibbs free energy through this relationship. I will write both representations. Or gamma I is going to be equal to exponential divided by RT. Now, if we have a mathematical relationship for the excess Gibbs free energy, we can estimate gamma I, or if we have an empirical relationship for the excess Gibbs free energy, we can still estimate gamma I, or we can estimate gamma I activity coefficient from the equations of state. And in a moment, we are going to look at some activity coefficient models, their implications in relation to the equations of state. So let us start again from our activity coefficient definitions. I have written the two basic activity coefficient models, one constant Margulis and two constant Margulis expressions on the board to have a little bit more smooth discussion of how we start and how we arrive at the models to begin with. So this one constant modulus expression starts with a total excess Gibbs free energy of having a constant A multiplied by x1 multiplied by x2. So we are talking about a binary mixture. We have species 1 and species 2, and this expression has zero excess Gibbs free energy at both pure fluid coordinates. If we have pure 1, x2 is 0, which makes the total excess Gibbs free energy 0. If you have pure component 2, x1 is 0, and total excess Gibbs free energy is 0. Taking this and using the definition of partial molar property, we're going to take the derivative of this function with respect to 1, with respect to 2, component 1 and component 2, to obtain partial molar excess Gibbs free energies, which is going to be equal to RTLN gamma I. So here I will attempt showing how one constant modulus is being translated into the activity coefficient relationships. G1 excess partial is going to be del over del n1 of total, and total is n times theta, right? So this is going to be equal to, as we have done in the beginning of this recording, del n over del n1 times g excess plus n times del g excess over del n1. Remember that this was 1 because n was n1 plus n2, and these partial derivatives are taken by keeping temperature, pressure, and others constant, other component amounts constant. So this is going to be 1, so we have g excess plus n times del g excess times del n1, del over del n1. Now we are going to substitute one constant modulus a x1 is equal to n1 over n1 plus n2. This is x1, and x2 is equal to n2 over n1 plus n2. Or simply, we can just disregard the second term in the denominator, combine these two. So we are going to take the derivative of this group with respect to n1. This is equal to g excess plus n times a times, we're going to take the derivative of a ratio n2 multiplied by n1 plus n2 square, right, minus n1 times n2 times 2 times n1 plus n2. Divided by n1 plus n2 raised to the power 4. So again, this is going to be a complex, not in the sense that it is difficult, in the sense that it is going to be tedious. I'm not going to conduct the algebra here, but from the algebra, eventually we are going to lose this g-excess. We are going to recover the g-excess as one of the terms, and we are going to cancel this, and the second term is going to take us to x2 square. And taking the derivative with respect to the second component is going to take us to the second activity coefficient relationship. So what is unique about the one constant modulus is we have established the zero excess Gibbs free energies at the intercepts, at the coordinates where we have pure species. The second thing is that it is symmetric. All right, we have only one constant, and while the activity coefficient of one component is decreasing, the activity coefficient of the other component is increasing. All right? Yeah. And symmetry is not always the case that we observe in nature, and in order to take care of the asymmetry, we need additional constants, additional parameters. So for that, I put on the screen two constant modulus, activity coefficient relationship. So we have, in fact, we have 4 constants, 2 for each. We have alpha 1, beta 1, alpha 2, beta 2, which are dependent on 2 different constants. They are derived from the Redlich-Kistler expansion. So keep the Redlich-Kistler expansion in mind. We have seen this before, but now we are going to pay a little bit more attention to what the prediction of the Redlich-Kistler expansion is. Here we start from the excess total Gibbs free energy of the mixture as a general x1 times x2 term. All right. One constant, it was the first term that we have taken, the constant term. The 2 constant comes from the first 2 terms. Now we have A, we have B, and B takes care of the influences of the difference between the mole fractions of the components. So this introduces a bit of asymmetry in the prediction of the activity coefficient. And of course, we can just go 2, 3, and so on and so forth if we need more precision in our predictions. So this summarizes the concept of the activity coefficient. The activity coefficient is an empirical relationship, highly empirical relationship. We have to rely on the experimental measurements of the volume changes and in many cases, enthalpy changes also. So with that, we will now be able to start making predictions of the real fluid vapor liquid equilibrium estimations.